Yeah, my name is Rene. Welcome to the session. This session is about mobile mixed reality, or how you can leverage your existing assets. And Thomas introduced me, I'm working with Valorem, and we have been doing HoloLens development since over 2 years now. We were one of the first partners that Microsoft invited to get access to the hardware and the SDK. And since then, we developed a bunch of solutions, like dozens of those for different clients, big companies in the automotive and engineering field. And typically, they have existing assets, right? They have existing 3D models. And what we hear all the time is oh, we have those models, you can just reuse them, right? Which is never the case, because it just not works like that, especially when we're targeting mobile devices, like a HoloLens, like a Gear VR, Daydream, or Oculus Go, and all those mobile devices. Because the trend is really going into untethered, full contained devices, which of course has not your full computing power of your desktop PC, right? So in the short time we have here, because this talk is just 15 minutes, I'm trying to run through that, and we will maybe have some question time at the end. Good thing is there's no other speaker after me, so I might go a bit over that. Sorry. Yeah. All right, so let's get started. So why is mobile a challenge? Well, we have limited hardware. We have a limited memory, we have limited shading units, and so on, right? So we really target a mobile device. Another thing is we have highly tessellation is very expensive. So let me step back for a second what tessellation means. So when we deal with CAD models, they are represented in a different way than actually modern graphics cards render 3D content. So graphics card render content, they understand vertices, they understand points, and then connected them as triangles, and then they form a mesh, right? That's what a graphics card understand. But typically in a CAD program, in a CAD world, those models are represented in a parametric fashion. So they are represented, for example, let me give you an example, a beam, which is a cylinder, right? The cylinder is represented as a point in 3D, the length, the extruding, and the radius and diameter. That's how a CAD program typically represents it internally. But in order to render it, you need to convert that from this representation into a geometry and a tessellation. That's the tessellation step, right? Converting that. So if you have lots of those triangles and have a high tessellated model, it's very expensive, because a modern mobile graphics card especially, they usually render 16 pixels at once. So if you have a triangle which is smaller than 16 pixels, you're overshading that batch, right? So that is important, that you don't have such high tessellated models. Limited draw calls is another thing. It's really easy to convert a CAD format into a geometry that is like an FBX, OBJ, OBJ file. But the challenge is really, reducing like I said, the tessellation level, but also the hierarchy. So if you just convert that and have all those separate items, let me give you another example. Think about an architectural building, right? You can have all those pieces could be separate in the hierarchy. And then if you pass them on as separate meshes with their own textures, that's very expensive, because you have lots of state changes in a graphics card. So another way of optimizing that is merging that together, merging geometry together in one bigger mesh, or groups of that, and also the textures. And there are ways of doing that, which I will talk about. Yeah, the main important goal is reducing the data, because if we have a 30 million polygon model, you cannot just render that on a mobile device. You cannot render that on a HoloLens. It's just not going to work. It might work. It will probably crash, or the frame rate will be so bad it's not a user experience you want to target, right? So what can you do? Of course, the first thing you can do is you can reduce the data during the tessellation phase, which means converting the CAD model from your CAD representation into the geometry data. And programs like Autodesk Inventor or other CAD programs, of course, they have an export format for converting from this internal representation into an FBX or OBJ file. And for Autodesk Inventor, for example, you can define the level of detail. So you can say, okay, I want this and that level of detail. So you can define the tessellation rate. But typically, what we encounter is the clients, they don't want to give us the original models. They don't want to give us their CAD models. There are multiple reasons for that. So we have to deal with already converted models. We have to deal with already tessellated models. So that's why we will focus in this talk about the post-tessellation steps. You can do it manually, and you can do it automatic, and you can also do no optimization and actually offload the rendering, right? So what can you do for manual model reduction? Well, that's rather straightforward, right? You can take a 3D artist, a 3D modeler, and he can take a model and optimize it by hand. This will, of course, introduce and result in the best quality, but it's highly expensive, of course, right? Labor-intensive work, and it doesn't scale. So that's the issue, but of course, they can be supported by tools like, authoring tools, typically Maya, 3ds Max, and so on. They have included tools that support a 3D artist doing that. And there are also specialized tools on the market. One of them is Pixies. There are a bunch of others. Pixies is really promising, so if you want to do like manual model reduction but don't spend too much time, take a look into that tool. Like I said, very labor intensive, but the benefit, of course, is it's a human, right? Your 3D artist, that's a human, so he can talk with the subject matter expert at the client. And they might tell them, okay, guys, we're not interested into all those balls and screws in our model. We don't care about that. You can remove all of them, right? And automatic reduction wouldn't know about that, so they would just reduce all of them, and then the overall total count of triangles is, of course, affected by that. So automatic reduction is important because manual model optimization is not always a way you can go because of cost, and it doesn't scale. If you have thousands of geometry models or thousands of CAD models to optimize, well, you cannot hire 1,000 3D artists, right? That's just not going to work. So what can you do? There are tools on the market. The two major ones are Simplygon and Umbra. Simplygon was this year acquired by Microsoft, and they're building an Azure pipeline around that, which is rather amazing. So keep an eye on that. There's lots of stuff I cannot talk about, but there's a lot of interesting things that will happen in space. Umbra from Finland, also a very good tool. It also supports the typical things which I will talk about. Very good tooling. They're on the market since quite a while, and they're really pushing They're really pushing forward on that. And I will show you a video of that in action. You can see the screenshot. I will also show that in a video later, but what are the tools doing? Well, first of all, there's a concept called level of detail. Simplygon, for example, they create static representation of different level of details. So they will give you a model which is like, instead of the 30 million polygon, you will have one which is 10 million, and you will have one which is 1 million and one that is 1,000 or something. And then it will pick, depending on the view, like how close you are, right? It will choose the right model. Umbra does a different approach. They use dynamic level of detail, so they're actually not using the whole mesh as once, but they're actually looking into the separate pieces. I will explain that in the video. Occlusion culling is also important, so think about a scene where you have a city rendering and you have lots of skyscrapers, right? And so the skyscrapers in front might hide the things that are behind it. So why pass the geometry actually onto the graphics card? There's no reason, because it's hidden. This is the concept of occlusion culling, right? Remove that which is occluded. Umbra supports that as well. Streaming is also a thing that Umbra supports, so think about even if you have reduced a ginormous amount of data, you still need to render it, and you still need to bring it in. Even if it's dynamic level of detail, you still need to transport it to the graphics card, because you cannot load everything into the graphics memory. It's limited. So what you can do with Umbra, they can stream it from the disk of the device, and they can even stream it over the network. It's pretty cool. All right, let's take a look at the video here. This is a 30 million polygon model originally. And it's just a quick recording. And this is where the level of detail kicks in. So I'm looking a bit longer at the model, and then it dynamically loads that. And you see this was a couple of months old when I did that with an earlier version of Umbra. It's been a while since then. It's much faster now, so they can fill in and dynamically load the data much quicker. But you can see, like, if I watch at the bridge, it takes a couple of seconds, fills in the data. There you go. And then we have a higher level of detail, right? And this scene is also nicely done because it has the occlusion culling kicking in. We have lots of those skyscrapers, like all the geometry behind that is actually not being rendered. How does it compare? So this is the original. I just picked out one of the client examples, like that was from a building. So this is actually a beam, right? A beam inside a building. And so the automatic reduction, where this version was done, the research was done with Simplygon, I think. So of course you can see it, the original model highly tessellated. So lots of small triangles here. Well, you can hardly see it here on the presentation, but these are all small triangles. And then the automatic reduction reduces it to much less triangles, but also introduces some artifacts, as you can see here. So what would a 3D artist do? And this is really a client example, right, where we worked with them. Well, my 3D artist, what he did is, well, he reduced it to this. because it's just a cube, an extruded cube, right? It's 12 triangles compared to thousands. Because he talked with the client, and they told him, well, we're really not interested in the roundings of those beams. They just need to be visible somehow. So, well, reduce them to the maximum you can, right? Another example, original model, automatic reduction. It's pretty good. It's actually not bad. You see here's a small artifact, but that's not a big deal. Yeah, manual reduction would like really introduce a sharp edge here and get rid of a bunch of more triangles. All right, so what is no model reduction? So what you can also do is you can take your original model and render that not on a mobile device, but actually on an external computer, for example. There are a bunch of solutions for different devices. For the HoloLens, there's one which is called holographic remuting. And what it does, it renders your whole scene on an external computer. So this could be like a full-blown desktop PC with an NVIDIA 1080, whatnot. It can render your whole model, and you can reuse your whole model, plus also add some effects which you could never render on a mobile device, which are very expensive, like screen space effects, like depth of field, and all those nice little details, right? You can have them render on an external device. So what's the issue here? Well, you have introduced latency. For holographic remuting, what it does basically, so you wear the HoloLens, and the HoloLens gives you the positional and the rotational data of the device, plus the gestures and all the input data. That is sent from the HoloLens via Wi-Fi to the computer. The computer recomputes the scene, it renders the frames for the left and the right eye, streams that as two video streams back to the device, right? So you can imagine there's a latency introduced. If you have good Wi-Fi equipment, you can get it down to 20 milliseconds, which is acceptable for static scenes. So this is really a solution when you, for example, have large architectural review meetings where you just want to see a static model with not a lot of animations, no dynamic stuff, but mostly static, maybe some animations, but you can deal with 20 milliseconds latency easily there. So that's definitely a solution, quick and easy, because it's really not expensive, right? You can just take the original model, set it up correctly, and works well for static scenes. So let's come to the conclusion. What should you choose? Well, the typical answer in IT and computer science is like, it depends. And it always depends, right? On what? Well, quality versus budget. If you have unlimited budget, manual model reduction, right? If you have unlimited resources, well, go with that. Best quality. But typically you don't have that. So another metric could be the model itself, of course. So we did some research for multiple clients. How can we build an automatic processing pipeline and things like that? What we found out is like for most models, we're especially targeting architectural models in that case study, 5 to 10% of the original size. So if you take a 10 million polygon model and reduce that to 100,000, that's not going to look good. But if you take a 1 million polygon model and reduce it to 100,000, so you can render it on the HoloLens, for example, that looks actually pretty decent for most models. So that's a good indicator. Of course, occlusion, like I said, occlusion culling. If you have lots of transparency in your scene, you don't have occlusion culling. Or if you don't have lots of like skyscrapers as a good example, if you don't have that, well, you don't have a benefit of occlusion culling. So that's another thing. And modeling quality is also very important because, well, it depends how the CAD program exported the format. It can introduce holes and other kind of issues into that export. Because as with typically, I mean, there's FBX and OBJ standard, but as it is with every standard, like every company implements it their own way. So it's kind of, sometimes you have really bad exports. So modeling quality is an important piece. Interactivity, so I touched that. If you don't have lots of interactions, not a lot of dynamic stuff going on, well, you might actually want to do no model reduction. Hybrid approach is also something you can consider. For example, we worked with a client. They had thousands of CAD models, so we could build them a processing pipeline, which is reducing 95% of their models. But 5% of their models are too complex. So you could output them, and then you could have someone take manual steps to do that, or do some hybrid approaches there, where you can actually include SDKs of the CAD programs to do some automatic reduction. Autodesk Inventor has an API, for example. So there are some ways to build this automatic as a pipeline and combine all of those approaches. The main conclusion, there's no magic button at the moment. There's really no magic button which you can just press, okay, I want to have that automatic reduction, I want to have that amazing model, it should look like the original one, but it should be on my mobile device. Well, when I say there's no magic button, not yet, what I especially mean is, well, we live in a, kind of this nice, time where we have things like mixed reality, augmented reality, and so on, which provide us all the nice visuals. But the another amazing part right now is really AI, machine learning, especially deep neural networks. And there's really a lot of movement in the industry right now, also with 3D computer graphics. There was just recently a paper released by Autodesk where they trained a neural network on a couple of automotive models. And the neural network and autoencoder actually generalized on that. And now it can produce any new automotive models using the 3D content. Another amazing paper was done by the guys from Princeton. They did a paper where they can fill in missing sparse voxel data. So basically you have a depth camera, right? And the depth camera only sees what it can see, but it cannot look behind the stuff. So, but you also want to have your full 3D model of that. So what they did is they trained a neural network for different interior settings, and it can fill in those missing data. So it can fill in those missing pieces. So why actually not build a neural network that can optimize, for example, it's trained just for car engines, right? It learned how to optimize 3D car models, or just car engines, or just one is trained for specific tasks like houses and so on. So there's a lot of movement in the industry, and I'm pretty sure this will be solved in a couple of years, that you have really a full automatic pipeline that looks really decent. All right, thanks for your attention. You are probably all hungry and want to get some lunch, so I will also be around for the whole conference, so till tomorrow, so feel free to find me somewhere and ask me. You can also reach out on Twitter and whatnot, and yeah, thanks for your attention.